FPGA. Fine. So morning session, first session we have seen how why we have to use lab FPGA. What is the use of what is the advantage of using lab FPGA, and we have seen that how lab FPGA program is going to help us to solve a critical based application problem. Just a minute, I'm getting some disturbance. Sorry for the disturbance. So and then we have discussed about like how we can develop FPGA based applications, and we have seen few scenarios also. Fine. So now I'll be showing another video. So which the application was completely developed by using LabURT and FPGA. So I'll be switching to the another PC. Just a minute. So, and in the second session, we have seen how to create a project and how to add the respective remote target to your existing project. And then we have seen how we have to add FPGA target with your existing projects, right? And then we have added a VI, and after that, we have seen how we can develop applications, okay, using LabURT and FPGA, fine. So these are the things we have discussed, and we have seen what are the different steps which will happen whenever we try to compile the program. Okay, so right now we are going to see a small application. So let me switch to another system. Just a moment. So here, I'll share the screen. Okay, I hope you people can see my screen. Yes. So now I'm going to play a video, so which was completely developed by NI LabVIEW and then NI Hardware's Compact Rio. Okay, so it's a four-wheel hybrid mobile robot. Okay, you can see here. It does not have any audio. Okay, so this is the layout, and see, so this one, so they're trying to control through wireless mode, and this has been completely developed by using a compact Rio, so which we are learning about Rio programming, right? So here they have used LabVIEW FPGA and LabVIEW RT. Okay, so this is the front panel of the respective application. See, you can see now it is in wheel mode. Okay, so they are controlling this through Wi-Fi. Now it is transforming to leg mode. So it is going to walk now. So now it is just climbing the modes. It is like this is how they'll test whether it has a possibility to climb the stairs. Yes. So this is about the one of the concept which was developed by NI hardware and NI software. Just a moment. There was a network issue here in another system. I'll try to rectify that. See, like this, you can create n number of applications using NI hardware. Even if you want, I can show another one, which is going to be fault identification in the grid. Okay, right? We can just have a look on this. Talk about a couple of those technologies, particularly around the smart grid and renewable energy. I'd like to welcome Principal Product Manager Brian McCleary. Hey, brother. How you doing, man? I'm very good. All right. Let's start with the smart grid. Tell us about the smart grid. Sure. The smart grid is going to revolutionize our energy system the way the internet revolutionized business. The main difference between a smart grid and a dumb grid is the sensors. In the dumb grid, the operators only know if there's a problem and the business is on the call. And to explain what I mean, let's take a look at our little significant village over here. Yep. So currently we're operating in dumb grid mode. The Department of Energy estimates that unplanned outages on our power grid cost the U.S. economy over $150 billion a year. So to show what I mean, if you would play the role of a force of nature for me there, Eric, and generate a fault on our grid, it's the force of nature. Okay, I pushed the tree button. The tree fell on the line, as you can hear. And we lost power to like half the city. Yeah,
we got a real problem here. All the lights are out for these houses. Our recloser has tripped off the power, so we're not going to have a fire on the lines. But we're going to have to wait for somebody to call this in, the utility to find and locate the problem. You get the idea. It's going to take a while to fix this. Yeah, see what you call the dumb grid. That's right. So what makes the smart grid smart? Well, if we would go ahead and switch our city here to smart grid mode. Nice touch. Welcome to Smartville. Okay, never another phone here, right? Yeah, give me a phone. Same screen, same line. That's right. So as you can see now in the smart grid, our smart switching devices have actually rerouted power from the second substation here to all the customers that can receive it. You see there's a small section of the grid that the power is still out, but we've been able to restore power to most of the customers. That's cool. And this is really enabled by these compact real smart switching devices that are able to monitor the power, detect the problem, and actually the utility is going to be able to fix it faster because it's already send us a command or a signal to the utility identifying the problem and telling them where to go to fix it. Okay, gotcha. Now, Ben, I noticed when I walked onto the stage, there's a huge piece of electrical power equipment down there. Tell us a little about that.
Sure, it's a smart switch device developed by Siemens in collaboration with National Instruments and CenterPoint Energy, the third largest energy utility in the U.S. Essentially what it does is it monitors the flow of power on a pole, and if there's a problem, it will alert the utility so they can shut down the power. In the heart of that smart switch, though, we have a compact Rio that's monitoring the flow of three-phase AC power. It's controlling the vacuum breaker that can shut off the 13.8 kilovolts, and it's streaming that back to the utility over a redundant wireless grid. And actually, in the future, when there's a fault, it'll be able to use some adaptive pattern matching and figure out what that fault is and actually tell the utility more information. Cool.
One of the areas where Rio
So this is one real-time application which they have implemented for smart grid. They have used compact Rio systems. Okay, so in order to find the fault identification, fine. So now let me just connect through my system so that we can start to develop the code. Fine. So if you have any queries regarding the previous session, so you can ask me. So I'm ready to clarify your doubts. Okay, so now let me share the screen also. Stop the screen in another system. And now my voice is audible and you can see my screen also. Yes, okay. So right now we are going to develop applications, okay, using LabVIEW FPGA. Fine. So now we are going to see a new concept. Okay, so how we can transfer the data. Okay, how we can transfer the data from FPGA to the RT. Okay, so from FPGA to RT, even from RT, if you want to transfer any data to PC also, that is also possible by using shared variable concepts. Fine. So now we are going to learn how we are going to have a data transfer, okay, between different targets here. Okay, so one is going to be LabVIEW target and another one is going to be, okay, RT target. And as we discussed about this FPGA, right, the most advantage of having this FPGA program is what we can go for parallelism. Okay, so how we can achieve this parallelism? So parallel operation. So by having this option, okay, about parallelism only, FPGA is considered as very powerful tool, okay, and technology. So when we go for parallel processing, right, so a standalone processor architecture, a parallel operation architecture, not truly parallel. Okay, fine. So parallel operation means you can use the same resource. Okay, you can use the same resource For example, because it doesn't field programmable gate array, so whenever we try to develop any logics, right, each and every logics will be placed as a separate. Okay, it's going to convert into a VHDL, and then it is going for routing and mapping, where each and everything will be arranged separately in the field programmable gate array, where it is not going to use the same resource. Okay, if we go for an operating system, right, that operating system should share the processor for multiple application, which is not okay. So an efficient way to develop a standalone system or real-time application. So in those cases, we can go for FPGA-based applications, right? So in FPGA-based parallel functions and loop executes through parallelism. Okay. So another advantage of running the code in parallel is you can use some section. Okay, you can use some section of code. Okay. So which, for example, if you want to acquire, okay, think that you want to acquire a sine wave, or if you're going to acquire a continuous signal with a high faster rate. Okay, at the same time you want to generate some pulses. Okay, so the frequency is going to be different. For sampling frequency is going to be one frequency that will be different, and when you want to generate a pulses, we have to provide the switching frequency that is also going to be different. Okay, so in those cases and all, you can go for parallel processing, where each and every task will not get disturbed, and it is going to perform its operation on its own. Okay, so because everything is happening inside the hardware, so we'll not have any problem. Okay, so that is the most advantage of using FPGA based program. Fine. So when you're going to use FPGA hardware, right, so in order to time loop for each and others, okay, so we can affect the execution order. Fine. So if you are going to have a continuous acquisition, if you are going to have a continuous acquisition, right, so where we know that always the output of the FPGA is going to be a fixed point numbers. Okay, so think that if you're going to measure a value from a temperature sensor, where continuous acquisition is not required, because only whenever the temperature changes, the output from the sensor is also going to change. But think if you're going to measure a ECG signal or a EMG signal, okay, a biomedical based signal or a communication based signal or an audio signal, for each and every instant, okay, the output will be keep on changing continuously with respect to time. In all those cases, when you go for RT, okay, so RT cannot acquire continuous sample. RT can acquire only one sample. RT means your processor. Okay, so in those cases where processor will we cannot be used in an effective way, so we have to go for FPGA. Okay, we have to go for FPGA. So when we want to use FPGAs, right? So we have to use what buffers. Okay, so we have to use buffers. We have to go for a buffered data concept, so that each and every data will be collected and that will be stored in the buffer. And from RT, we can get the data from the buffer and we can process it, where our entire application will not be get disturbed. Okay, so in order to have a transferring of buffer data, okay, so between different portions of FPGA BIs, okay, we can use what FIFO. Okay, so FIFO is first in first out buffer, right, where the first data item which is stored inside the memory, okay, will be the first item which will be removed from the memory here. Fine. So if we go for FPGA FIFO functions, right, so if you're aware of queue concepts in LabVIEW, okay, so because few people have very good knowledge on the LabVIEW core and Goto, we have a concept called queue, where in order to avoid the data loss, we will be storing all the data inside the queue, and with the help of references, we will be taking the data one by one. Okay, so in the same way, FPGA FIFO function also, okay, functions like a length of queue, where multiple data items can be written and to the memory, and we can read the data from the memory here. But if you see, unlike a queue, okay, so FPGA FIFO will always ensure a deterministic behavior, where there will not be any data miss. Okay, we will not miss any data here. Okay, because we are going to imposing a size restriction on the data. Okay, and both the reader and the writer can access the data simultaneously. For example, whenever it is keep on writing or storing the data inside the memory, at that same instant itself, we can get read the data from the memory here. Okay, so we'll see how we can include FIFO. Okay, how we can include FIFO memory, right, and how we can store the data and how we can access it in your RT during this application development. Okay, so when we talk about FPGA FIFOs, right? So if you want to create a FIFO, okay, so we have to create a FIFO on target scope, or else we have to create on VI define, or else DMA. So I'll tell you how to create a FIFO. So right now, first we will add a target. So I click on the project, new, go for target and devices, and select new target and device, expand my area. Okay, I have opened in another new project. Yes, okay. So let me next add the FPGA targets. So right click new. You can go for FPGA target. Yes. So once we add an FPGA target, okay. So I'll just save the project now and go for another ALSGIT. LPGA and here the project will be saved. Let me take the accelerometer value. So I'll give ACC project. Okay. And now I'm going to add FPGA target here. So right click new. So to show you, okay, the already we have added the FPGA target. I can right click and add VI. Okay. So I have added a VI under FPGA. So I can save this VI ACC data. Okay, so even the VI is also saved here. You can just have a look. Right. So I have added created a new project. I have added an RT target, and then I have added an FPGA target also under FPGA. I have added a VI, that is ACC data. Okay, so now I'm going to store. Okay, I'm going to store the accelerometer values. So we know acceleration is going to be a continuous signal which will keep on changing whenever there is a vibration. Okay, fine. So in order to acquire the data continuously, okay, so we should not miss any data. Think that you are going to place an accelerometer on a motor where you're going to you acquire the vibration. Okay, it is like a health monitoring system of a machine, right? So we want to monitor the information continuously. So in those cases where RT is not a right choice to develop the application, so we have to go for FPGA based application where I'm going to acquire the information from a sound and vibration module. Okay, if you have a sound and vibration module, which will help us to measure the data from the vibration sensors, right? So to get all the data, we need to create a FIFO memory. Okay, next step is how we can create a FIFO memory. So right click on the FPGA target, new. Okay, so when you select new, see you will get multiple options here: library, class, FPGA FPGA base clock. Okay, see there is an option called FIFO. Select FIFO. Okay, once you select the FIFO, you will get this option. Okay, once you select the FIFO, you will get the option. There are three categories: general, data science, and then data type, and then interface. Okay, see the name is called FIFO. If you want to give any name, you can just provide here and here. Okay, so the types. Okay, you can see there is an option called type here. The first one which is showing on the screen is going to be target scope. Okay, so which one? The one which we see is what? Target scope. Fine. And you can see we have host to target. Okay, and then we have target to host. Okay, so now we are going to transfer the data from target to the host here. Okay, through DMA, right? So then we have to select what? Target to host. Fine. And if you see here, implementation is block memory, and the actual number of elements is going to be 1023. Fine. So we will see what are the different types here. First one we have seen is what? Target scope, right? If you see, the first one is going to be target scope. So whenever we select targets, right, we transfer a data from section of code in multiple VAs, okay, on a same target. But now we are going to transfer the data from FPGA to RT. Okay, so we should not use target scope. So whenever you want to have a data transfer on a multiple ways of same target. For example, if I'm going to use two different ways on the same under FPGA, In those cases, if I want to have a data transfer, I can go for target scope here. Okay, and if you see, we have another option which is VI define. Okay, so it is going to transfer the data to and from multiple loops within a single VI. Within a single VI, if you want to have a data transfer, you can make use of VI define. Okay, so and there is another option. Okay, so we have something called DMA is direct memory access. Okay, so which is used to transfer a data to RT host VIs from FPGA target. Okay, so then we have already chosen what target to host DMA, which means that we are going to transfer the data from FPGA target to host. Okay, now we'll consider our RT target as host now. Okay, right. So if you see here, under this FIFO, okay, if you see under this FIFO property dialog box here, right? So we have, okay, general, and we have data type, and then we have interface. When we select general category only, we'll get all these information here. Fine. So when I just go for data type, okay, when I just go for data type, sorry, when I go for general, so name, you can just give any name for your FIFO. Okay, so which appears on the project window. Once you provide a name and if you select okay, right, that name will be appeared on the project window here. Fine. And that whenever we just drag and drop and we'll put it in the block diagram, right, the name of the label will be displayed. And next one, type, we have to specify the FIFO type. Okay, target scope, we have posted to target. Okay, so we know target scope can be transferred, will be used to have a data transfer within FPGA VIs as well as, okay, but when you see, there is an option called host to target. Okay, host to target, which means that whenever you want to have a data transfer, okay, between host VA, for example, from RT to FPGA, from RT to FPGA, go for host to target. But now we are going to have a data transfer from FPGA to RT. That's why I'm using what target to host here. Fine. So these options we need to take care. Fine. And you can see, so number of elements requested. Okay, you can just provide the number of elements which the FIFO can hold here. Okay, so later part, the maximum number of elements which the FIFO holds, which depends upon the implementation whatever we select. Okay, and then if you see requested number of elements and actual number of elements here. Fine. So once we select the amount of space available, right, so it depends upon the implementation. Right, if the FPGA does not have enough space, okay, you can ask the question like, if the FPGA does not enough space, okay, for the requested number of elements, okay, so then FPGA will fails to compile and it is going to pop up an error. Fine, so which will tell you that it is not possible to have that much number of elements here. Fine. And if you see here, the DMA, okay, the DMA host to target, okay, or target to host, okay, which we will get in the pull down menu, the requested number of elements, right, we have to specify the FPGA part of DMA file here. Clear. And next one, see implementation block memory. Okay, so if we select a block memory in the implementation control, fine, if we select a block memory in the implementation control, right, the restrictions will be applied to the number of elements of FIFO which it can hold here. Fine. And if you see, the implementation is going to specify the storage of FIFO used in the FPGAs here. Fine. So next one, data type, you can specify the data type, whether it is I16, I8, U8, and you can see all belongs to integer data type. So whenever your output from the sensor is going to be positive and negative, you have to go for a signed integer. In case if it is going to provide output, okay, from like 0 to 5 or 0 to 10, in all those cases we can go for unsigned integer here. And if you see, there is an option called interface. Okay, there is an option called interface. Okay, so which you can see arbitrate if multiple requests is only a number of elements per write is going to be one. Every time when this going to write, this going to write one elements, okay, which you can provide here. Fine. So if you see general, right, so we already discussed about the lookup tables and all. Fine. So the next step is what? So if you go to the data type, so we know if it is I16, when I go for fixed point number, so you will get these many options. Okay. So fixed point number means you have to tell you whether it is signed, or unsigned, what is the word length, integer word length, and what is the minimum and maximum value. All those things you have to mention, okay, because only when I select this option only you're getting this subdivisions, okay. Encoding, so what encoding will do, it is going to set the binary encoding steps for the fixed point values. You can see signed and unsigned, okay. So whether it is a signed integer signed fixed point value or unsigned, you need to provide here word length and the maximum minimum range. All these things you need to specify, okay, fine. So if it is I16, you can select will not get any option. Next one is FIFO read and write here, okay. Next option is what? FIFO read and write. So for example, once the FIFO is created here, when I just drag the FIFO and if I place it here, this is how the FIFO memory looks, okay. This is how the FIFO looks in the block diagram, fine. So once I place it here, you can see the memory is configured and it is ready to store the elements here, right? So now we have to develop a logic to store the value, okay, inside the FIFO and in the in the RT target. So we can write, or we can, sorry, we have to read all the data, right, from your RT targets here. Clear? So now when I place this FIFO, I think we are going to have a continuous acquisition, okay. So I'm going to have a continuous acquisition here. So for that I have to use a while loop control, okay. And most when we develop an application, right, so we have a stop button here, and if I right click, most probably they'll have false because FPGA is going to, they wants the program to acquire continuously. And most of the time if you want to have a control, you can have a stop button, or else you can create a false constant where the acquisition will won't stop at any point of time here. Only thing is you can have a control on the RT target to analyze the values, fine. So now I'll go for a sequence structure because we want to do it in order to avoid the execution of two times. We already seen, right? So we have the recommended thing is what? So we have to use sequence structure, fine. And once I place the flat sequence structure, I need to have two frames, add frame after, okay. Right click, loop timer. So if you want to do 32-bit, let it be. If you want to have this in microsecond, you can just provide microsecond and provide OK, fine. And then right click, create control, okay. So where you can provide this value, okay. See, when we are going to acquire any continuous signal, right, so we have to go for sampling where you need to provide the sampling frequency, okay. So which, when we talk about time duration, is going to be the dt value between each and every samples over there. So that we have to provide through this control only, through your friend, through your RTVI, okay. That's why I'm just creating a control here instead of having a constant. And now if I want to measure the accelerometer values, FPGA IOs, input output nodes, place it on the block diagram. See, IO nodes. So onboard IO, you can select accelerometer x-axis. Now the data is going to be what? A fixed point number. Okay. So as we know, it's a fixed point number, and whenever there is a vibration or tilt, it is going to provide a value which I want to acquire continuously without any disturbance, fine. So then you can see here, so we have to write the data to the elements, okay. We have to write the data to the elements here, fine. Once we write the data to elements, so whatever the value which we are getting from the accelerometer, that will be stored inside the FIFO memory, okay. And see, there is an option called timeout create constant, okay. So let me give 500, fine. So it is used to check whether we are getting the data continuously. Fine. So next part, your coding is done as of now. So you can save the program. Okay. Once the program is saved, we need to compile. Okay. We have to go for compilation for process. Fine. So because your FPGA code is done, we are going to get an analog data from the accelerometer in case if you have connected any sensor or if you're going to measure, for example, think I'm going to acquire a communication signal, okay, or else I'm going to acquire a sine wave, okay. So sine wave is a continuous signal which is going to be keep on changing continuously with respect to time. So as I have to mention the sampling frequency for that position, right? So I'm going to use an analog input. So in those cases, what we will do, we'll use an analog input and that will be given to the FIFO memory. Fine. And then we have to go for compilation. Okay, we have to go for compilation here. So once we go for compilation, so click, it will ask you to compile because after generating the bit file only, with the help of the bit file, we can read the data from your in your RT target. Okay, sorry, we can read the data in your RT target. So it takes around 5 minutes for compilation. So in case if you people have an access to work with Rio hardware, so kindly try to learn how to develop an application using FPGA. Okay, and you can do your research work also. Whenever if you want to create a standalone application, whenever a time critical application comes into picture on priority, whenever you're having a prioritized based task, fine. So you can go for FPGA based program. Okay, so which will make our program to be very deterministic. Fine. So it's transferring the data to the compile server. Once it gets the information, yeah, see it started to generate xylene IP. See synthesis is over, then pre-synthesis, and then routing, placing and mapping. Okay. Finally, it is going to generate a big file. Fine. So we have to wait. So it has to compile. Around it takes around 6 to 7 minutes. So if you have system and if FPGA target is installed in your system, you can develop the code and you can also parallelly go for compilation process if you have FPGA because I have developed the code to acquire the data from the accelerometer. Maybe parallelly people can also develop the code in the system. So if any people is available in your institution and if you have new hardware, you can connect it with your laptop, try to read the data through accelerometer. So it's compiling. And we our hardware has audio input and audio output. So we can acquire an audio signal, we can process the audio signal. But when audio acquisition comes into picture, the best way is what we have to always go for FPGA because audio is a continuous signal which will be keep on changing continuously with respect to time. So the best thing is what go for optimization using FPGA and process in the RT. And if you want to send any audio command as an output, then again from RT that will be sent to FPGA. Okay, and then we'll get the output. We know output will be the audio information output will be in terms of fixed point number. Okay, and we have to go for the data conversion. So LSB weight into the raw data is equal to the voltage. So that and all we need to take that. Fine. compiling. We have to wait for a while. Keep on compiling on the same step. It takes much time because already now 4 minutes is over. It has to move to the next step. As we have FIFO memory, it's taking too much time. So because once it completes its compilation process, so then only we'll get the bit file, and then only we'll have an option to read the information or to access the data from the accelerometer from FPGA target to the RT target. Yeah, it has gone up to placing. So mapping, routing, then generating bit file. Only 3 steps are pending. So we have to just wait for a few more minutes. Yes, so placing is once it's over, so we 2 more steps. So then we have to develop the code in your in your RT, because then only we will get the bit file. So once we get the bit file, only we'll get all the references. That's why I have not developed the code in RT target. Okay, so you don't think that while during this compilation process itself, we can develop a code under RT. Okay, so we'll not get the references because the first function which we will use is to call our bit files. Okay, so we have to get the bit file, then only we'll get all the references properly. Fine. So we have used FIFO right now. Okay, we have not used the FIFO read. We have used the FIFO right now. Okay, so when we use FIFO write, we are going to put the data into the target FIFO. Okay, so we have to configure the FIFO method. So how we can do right click, select method, and we have to go for write. Okay, so when we go for FIFO in, we have to specify the FIFO. If we leave the FIFO unwired, okay, so it is going to give broken wire when we are not going to provide the timeout values. Fine. Yes, so it is generating a programming file. Finally, it is going to generate a bit file. Right. So if you see elements, so in the FIFO, right, and the block diagram, if you see here, it has write, next one is going to be the element. The element is going to what, specify the data which we want to store it in the FIFO. Here the element data type will be configured on the FIFO property, and you can see there is an option called timeout here. So this timeout specifies number of ticks, okay, number of clock ticks the FIFO function has to wait for available space in the FIFO. Okay, so in case if the FIFO is full, okay, in case if the FIFO is full, right, the value of -1, okay, which prevents the function from timing out, okay, a value of 0. So which means that indicates there is no wait. So it is going to write a constant of 0 to timeout if we use FIFO method node in single cycle time loop. Fine. So So compilation is over, I guess. Yes, finally it is finalizing the program file. So you can see timeout question mark. Uh, Sir, FIFO means first in first out. Yes, sir, correct. So timeout, the question mark, which is going to return true if the space in FIFO is not available. Okay, so before the function completes the execution. Yeah, see, it is preparing for interactive execution, but it will not run because the hardware, okay, which we have to connect here. See, LabVIEW FPGA software component, other components are following error. It could not establish the connections, okay, which is specified to the remote device here. Fine. So now I'll give OK, and now the bit file is generated. And the same morning, whatever I have explained here, see, we can see the configuration, estimation, okay, estimation, device utilization. All these things can be viewed using this report option. I'm going to give close now so that the bit file will be generated and you can save. We have already saved the program. In case if you have doubt, okay, you want to check whether the bit file is available. So test type desktop KLS GIT FPGA. See, accelerometer project FPGA bit file. Then we have the bit files available here. Okay. So once we had a bit file, okay, once we have a bit file, next step is we have to develop the logics. Okay, develop the logic in your RT target. Okay, so I'll minimize this. So if you want to develop the code, okay, if you want to develop the code under the RT target, so right click on RT my Rio target and you have to select new and click on new VI, and once you select this, a new VI will be added here. You can see accelerometer project dot LB project. It is under RT my Rio target. Now the code is not under FPGA, it's under RT target. Fine. So next thing, what we are going to do here, okay. So we are going to develop the code. So for that, I'll go to the block diagram. So once I go to the block diagram, first function, okay. The first function which we are going to call here is right click, and you can see FPGA interface. Okay, right click. There is an option called FPGA interface. When I select this FPGA interface, place my cursor on the FPGA interface. You can see I'm getting an option called Open FPGA VI reference. Okay, when I click on this Open FPGA VI reference, I have to place it here. Okay, and double click. Okay, once you double click, see it is asking to select build specification VI or bit file. Okay, I will select bit file and see. Okay, let's go to FPGA bit file, and you have to choose the bit file here. Okay, see, automatically these two options are enabled, dynamic mode and run the FPGA target, both are enabled, and then give OK. Fine, and then you have to select, right click on the resource name, create constant. Okay, you have to select your Rio hardware, FPGA target Rio here, because we have used simulated hardware. Okay, so we have to go for that option. Fine, so first your hardware is selected, next right click, and then go to my Rio. You go to my Rio, sorry, FPGA interface, and you can see there is an option called invoke node. Okay, there is an option called invoke node. Okay, so what we have to do, right? So when you go for this invoke node here, fine. So the next step, we have to just make use of the invoke node to transfer the data. Fine. So when we use the invoke node function here, so this invoke node function is going to invoke your FPGA interface method. Okay, or it is going to action on an FPGA VI. So you can just click on this. Okay, you'll get run You'll get abort, you can reset, acknowledge IRQ represents interrupt request. Okay, so wait for interrupt request. All these options will be available here. You can just create the reference FPGA reference out, and you can create this error in error out function. Okay, so initially we'll go for reset. Okay, so before trying to do any process, we'll initially reset it and then we can start. Fine. So I'll just keep it here, reset. Right. The next one, again we have to use invoke node. Okay, to run your FPGA target. Fine. To run your FPGA target, again make use of right click FPGA interface, and here invoke node, select here, connect, connect, run. Okay, see, wait until done, you'll get an option here. So now I'm going to select an invoke node which will run my text file over there. Fine. So if you want to have a label, right click, disable icon label. This one is open FPGA interface, which I put here. Okay. And now next we have to provide the sampling information. Okay, so next is what we need to provide the sampling frequency. So for that, right click FPGA interface. There is an option called read write control. Okay, there is an option called read write control. Connect it, the references, and connect your error in error out information and click. See, you have two options. One is to stop your program, another one is your count. Okay, so count is nothing but you can see the sampling frequency which we need to provide here, and it is configured in terms of millisecond. Again, it is configured in terms of millisecond here. So let it be placed as it is, and we know, so always it will accept your data in terms of fixed point number, and it should be in terms of microsecond. Okay, it should be in terms of microsecond, right? So what we will do, we'll create control in the front panel, a numeric control, and that is labeled as sampling frequency or sampling rate. That's better. We'll go for sampling rate. I'll place it here. Fine. And that sampling rate we have, because your time, the information to the loop timer will be in terms microsecond. You need to convert that into timing microsecond. So multi, first we have to inverse reciprocal. Okay, so once provide that, it will be into dt, and then multiply okay, create constant, so we have to convert in terms of microsecond. Okay, it's converted. Right, and I need to convert that into U32. Done. Connected. Okay, so we need to have a stop button. So if I want to do the program continuously, if I want to run the main thing is what we need to run the program continuously, so we have to use while loop. Okay, so we have just given the count, and what is the next step? we want to measure. Okay, what is the next step? Once we provide this, we have to read the data. Okay, we have to read the data, right? So for that, right click, we'll go for FPGA, and then you can see invoke node. Okay, place the invoke node, provide the reference here, FIFO. Okay, FIFO. Now we have to give FIFO read. Okay, we should not give FIFO write. We have to give FIFO read. Okay, so once you provide FIFO read, okay, once you provide your FIFO read here, right, you can just check the FIFO read, which is a FIFO read method, which is used to retrieve the data, okay, which is present inside the FIFO from another structure or another VI in the FPGA. Okay, the FIFO read method is going to read the oldest data in the FPGA. Okay, FPGA FIFO, and removes the elements from FIFO. What is the oldest data which has just received first in the FIFO memory, right? That data will be removed from the FIFO. So we have to configure the FIFO method node. How we can configure? By right click on the node, select method, and then you can go for read option. Okay. So when you just select it as FIFO read option, you will get multiple informations. So the first one is going to be FIFO in. Okay. So FIFO in specifies, okay, this FIFO, and if we leave the FIFO in as unwired, okay, if we leave the FIFO in as unwired, right, so we can specify the FIFO by right clicking on the FIFO method node and select FIFO from the shortcut menu. This is what we did once we place the invoke node. Okay, otherwise we can write a FIFO control, FIFO constant. Okay, next one, if you see, I have an option called timeout. Okay, what is the use of timeout? And the unit is in terms of millisecond. Okay, if you see the unit, which will be in terms of millisecond, right? So timeout specifies the number of clock ticks the function waits for available data in the FIFO. Okay, suppose if the FIFO is empty, a value of -1, which will prevents the function from timing out. Okay, so the function completes execution only when the data is available for reading here. Okay, the value, if you include 0, if you provide a value of 0, the function does not wait. Okay, and then wiring a 0 constitute to the timeout. Okay, if you use the FIFO method, that will use only for single cycle timed loop. Fine. If you see here, FIFO out is the reference which is going, okay, so which is going to provide the reference out over there, and we know the elements. Okay, we know the elements, so it is going to give the oldest data, which is the first data present inside the memory. Clear? So, and we have, whenever we have a problem, okay, so if suppose the FIFO overflow means if there is already all the data are occupied in the FIFO memory, and if any new data are coming in, okay, that's FIFO overflow. Underflow if there is no data here. Okay, so if there is a difference in the rate at which the data is written to the FIFO and the rate at which the rate at which the FIFO is read, right, then we have to face the error. Okay, if you have both the information, okay, if you provide both read and write with the same difference rate, we will not provide it, we will not face any problem. So if the write method occurs more often than the data is read, then the FIFO will eventually fill and overflow condition will occur. Okay. In case when the FIFO is full, okay, when the FIFO is full, additional write method timeout and data is not returned to FIFO until you get the space. Okay, until the space is available. Fine. So the space can be created by reading the data from the FIFO, okay, or by resetting the FIFO memory, right? If the read method occurs more often, okay, if the read method occurs more often than the data is written, obviously FIFO underflow will error will occur. Okay, so in order to avoid that, okay, in order to avoid that, when the FIFO is empty, the read method is going to provide what? Timeout. Fine. So that's why we have to provide a proper rate so that there will not be issue of override flow and sorry overflow and then underflow. Fine. So how it is going to communicate? Okay, next one is what communication between the host and the target here. Fine. How the FPGA and the RTVI can communicate. Fine. So we can programmatically interact with the FPGA VIs. Okay, You- we can programmatically interact with this FPGA VI using a separate VI running on the host computer. Okay, see what is the host now? RT is the host which we are developing the logics. Okay, where we are going to develop the logics here. Fine. If you see, we are going to just get the bit file from your open FPGA interface, right? So the programmable FPGA interface communication differs from interactive front panel communication because it requires you to create a host VI as well as an FPGA VI. Okay, so whenever we use the programmatical FPGA interface communication, right? The FPGA VA runs on the target and the host VA runs on the host computer. Fine. So we use a host VI to send the information between host computer and the FPGA target. Okay. So when you want to do more data processing, okay, then you can fit on FPGA. Then you can go for this communication between host and target. See, whenever we develop more number of logics on the FPGA target, it occupies more gates over there, and the compilation process, everything is going to be. It takes much time. So when your application, which portion of the application is critical, right? So only those portion of codes we can develop in the FPGA, and the analysis can be taken care by RT here. Okay, see whenever you want to do any perform any operation not available on FPGA target, right? So like numeric arithmetic calculation, okay, so those kind of things can be done in host, and you can push it into the FPGA. Okay, and then if you want to create a multi-tied application with FPGA targets, okay, we can go for it. Or if you want a long data, or if you want to control timing and the sequence of data transfer and all, so we can go for ask host to target communication or target to host communication. Okay, fine. So the host computer can be a Windows based computer or it can be a MyRio RT target. Okay, so both Windows operating system and the OS which supports the FPGA interface functions, right? Because it is going to support. In addition, we can use FPGA target interface function on the RT target to communicate with the FPGA, right? So if you see, when we use the FPGA VIs and functions to communicate with FPGA VIs from the host VI, the VI that runs on the FPGA target is called FPGA VIs here, okay? And the host VI. So now we have developed the logic, right? That is called as host VI, and that communicates with your FPGA VIs to control the FPGA targets. Fine. So the host VI will run on the computer or it will run on the RT target. Okay, it depends on the requirement. Either you can, if you are going to make a standalone system, it's better you can just develop a logic under RT itself. In case if you want to send any command from your system, if you want to monitor the information remotely, so you can have your host computer, and from computer you can transfer the data to host and then to FPGA. That is also possible. Fine. So there are a lot of ways to have a communication between host to target. Right now our target is FPGA, host is going to be the RT target. Fine. So we can establish and terminate the communication with the FPGA. Simple, download the bit file and we have to just reset, okay, and run the FPGA PI, right? And we have to use read and write data functions for the FPGA PIs. Once we get the acknowledgement, we can read the data from the FIFO here. Okay, so next we are going to have transferring the data. Okay, next is what? Transferring the data. For that, we will be using what? Read write function, which is available in your FPGA interface. Okay, simple item label, read write control. This is already an invoke node, which we are going to read the data from the FIFO memory. Okay, fine. So if you see here, next step is what? We have just developed the code, right? So we have to transfer the data, right? So front, and now we got the number of elements to read. Okay, you have to tell you how much number of elements you have to read here. We know the size itself, what it is, 1023. We can read 20,000 data. Okay, and this will be the data which we will get here. It's a fixed point number. Okay, so that if if you want to convert into acceleration, okay, that if you want to convert into acceleration, we know the calculation raw data into LSB. Okay, so we have to provide raw data into 3.906. Okay, 3.906 mg. So I'll convert that into dBl first. dBl, do double precision floating point number, multiply. I'll go for a constant 3.906. Okay, so we'll get the data, right? So that data, you can just put it in a waveform, or you can put it in a waveform graph, or else you can put it in a waveform chart. Okay, so if you want to see the data, I can put it here. So this one, AC, you can just have fixed point data which will come from FPGA. Okay, and this information you can just plot it in the waveform graph, right? And finally, right click FPGA interface, go for close. Okay, so this is used to close the reference. You can connect here, and to run the program of while loop. Okay, and to stop a program, we have a conditional terminal. You can just place it here, control stop button, connect it properly. Connect. Okay, so our code is done, and if we run the code, we will not get the output because we don't have the target label. And check here. Okay. So this is how we can develop the logics where we can have a data transfer from your LabVIEW FPGA to RT. Okay, so through this FIFO. Okay, so whenever you have continuous data transfer, okay, so what we can do is, okay, whenever we want to have a transfer the latest data, so we can send the configuration parameters or data from the host to FPGA, okay, and report the status from FPGA to host, and we can send the command C stop command and the sampling rate, whatever which rate we want to acquire. All those informations we are just sending it from RT. Okay, we're sending it from RT so that your FPGA will get configured. Okay, and we can have a transfer single point data between the host and the FPGA, and we can create test bed for FPGA. Yes, we know we have to use read and write control function in the host VI, okay, to access the data from the FPGA. We can go for read. If we go for write, we can write the data from your host target to the FPGA here. Okay, so an advantage of programming front panel communication, okay, relative to another method of transferring the data here between FPGA and host is very easy. Okay, and you can see here we cannot attain a high throughput with the programmatic front panel communication. Each call to the read and write function, which is going to initiate the data transfer, okay, with a very minimal delay here. Fine. If you see here, the read and write control functions, okay, the read and write control functions, which is going to read the value, okay, or it is going to write the value to the controller indicator in the FPGA. See here, when I just go for this read and write, I have only two controls, which means we are going to write the information from your host to target. Okay, if you see a host VI, this is the host VI now. I'll save this. Okay, if you see here, the host VI, okay, the host VI can control, it can monitor the data passes through the FPGA VI front panel. Okay, the only thing is we cannot access the value on any wires on the FPGA block diagram. Okay, because so it do not have any control of indicator unless the data is stored in the DMA FIFO. DMA FIFO is what? A dynamic memory access FIFO, which will help us for buffered data transfer. Okay, so what is the sequence here? We have to open the first FPGA VI reference function to open the reference to the FPGA target. Okay, then we have to use what? We have to write the FPGA VI reference out parameter to read and write control. Okay, before that we'll be using an invoke node. Okay, to reset and to run. Okay, and then we are going to give this to the read write function to access the controls and indicator on the FPGA VIs. Okay, so we can read the values from the indicator and we can write the control. Okay, both can be possible simultaneously. Fine. So we can then we'll be using invoke method functions, right? So invoke method functions, which is used to invoke your FPGA interface methods. Fine. So and finally make use of this FIFO. See, if you're not going to use FIFO, this invoke node is not required. Okay, so when I just right click, see, I have an option called run, abort, reset, wait, right? In case if you're not having a buffer data acquisition, only you want to read the data directly, you can just first place an open FPGA interface, and then you can go for invoke node. Okay, invoke node to reset, and then run, and then you can directly place your read write control. And instead of, if there is indicator, okay, if you see in the FPGA VI, we don't have any indicators. In case if you have an indicator over there, that label will be displayed in your read write control here, and we can get those data from FPGA and we can process it. But now we are going for a continuous buffered acquisition, right? So that's why I used a FIFO, and that FIFO is configured target to host. Okay, so and that's why here I am getting FIFO read. There, if you see in FPGA, that will be FIFO, right? And here we need to specify number of elements to read, and we have to get the data, and that data is a fixed point number. And the most important thing is we have to go for the conversion or the calculation, so which we have discussed in the morning session. See, so we have to for accelerometer, LSB weight is going to be 3.96. In case if you're going to measure any audio and analog input signal, okay, through MSB, then LSB is going to be 4.883 millivolts. Okay, that we need to provide. And if you multiply, okay, and if you're going to get the fixed point numbers, make sure you have to go for data conversion, or else we will get the coercion dot. Okay, so I hope people know already what coercion dot is. So coercion dot refers to the a temporary buffer will be created whenever there is a mismatch of data type. That's why I use this conversion number, okay, number conversion function to DBL. Okay, it's 2 DBL, 2 double precision value, and that fixed point number will be converted to DBL, and that will be multiplied with the LSB weight. So this is the one raw data into LSB is going to give your voltage information if it is analog input. As we have developed a logic to read the information from x-axis accelerometer. Okay, we'll get the accelerometer acceleration values in terms of mg. Okay, and finally, as we are going to run the program, or we are going to acquire the data continuously, I have just placed a while loop, and you can see one stop button is used to control, okay, to stop your FPGA VI as well as your main VI. See, when I just click on the stop button, that information will be returned to the FPGA VI, and that also will stop its acquisition at the same instant. And the main VI, which is the host VI here, which is under your RT target, that also will stop, okay, its acquisition, and will come out of execution here. Okay, and finally, if you see this close FPGA reference, which is used for closing the reference here, and if you go for right click, FPGA interface. Okay, see, this is the last one which will help us to close the FPGA interface here. Fine, so it will close the reference and it will come out of execution. So this is how we'll develop the logics to write the data from your host VI to the target FPGA target. At the same time, we can read the data from your FPGA to host VI. Okay, so if you have any doubts regarding this data transfer, please let me know. If you have any queries regarding the data transfer, please let me know. Any doubts, participants? Any queries, any doubts? Any doubts? Please let me know. Yes?
I think continue, sir.
Okay, fine. Right. So in this, if you want to have a data transfer, okay, if you want to have a data transfer, you can ask a question, sir, I want to have a data transfer between your computer. Okay, see, there are two different targets here in this FPGA, right? Two different targets in this project. One is your my computer. Okay, we have one hardware called MyRio. Inside MyRio, we have two targets. One is going to be your RT and another one is going to be FPGA. So now we have seen that how we can have a data transfer between your FPGA and RT. Okay, in case if you want to have a data transfer, okay, if you want to have a data transfer between your system, okay, your computer and then your RT target. Okay, so for else you are going to do some acquisition from FPGA and that will get processed in your RT. Okay, but in order to send some values from you want to monitor from your remote place through your computer, then you should have a data transfer between your computer and the RT targets. Okay, so that whenever you try to transfer any data from your computer, that will be transferred to RT. From RT, that data will be moved to your FPGA targets. Okay, so that is also possible by having a shared variable concepts. So in LabVIEW, we have different types of variables are there. Like we have local variables, we have global variables, and then we have network shared variables. Okay, so whenever if we want to transfer any data on a single VI, okay, on a computer, okay, we can go for local variables. If you want to have a data transfer between two different VIs when both the program are executing, you have to go for global variables. Fine. And then if you want to have a data transfer between different targets, okay, so here if you see my computer, that's a laptop, okay, that's going to be one target, and my RT, okay, the entire Rio hardware is going to be another target, right? In those cases, if you want to have a data transfer, you have to use network shared variables. Okay, you have to use network shared variables. So that we can use it here. And whenever your IoT concept comes into picture, whenever you want to have a data transfer, okay, you can make use of the network shared variables to have a data transfer between your host, your computer, and then your RT target and then your RT target VI. Fine. So there are n number of options are available to have a data transfer mechanism between different targets. It depends upon your requirement. Fine. So I'll show a small video. It's about acquiring your eye movement. Okay. So I'll switch to the another system. Just a moment. Yes, it's available. So from here here I have to start my presentation. You can see my screen now. And now,
Yes, sir, we can see.
yeah,
Hey guys,
let's see.
welcome to Waterloo Labs. This time we're going to use electrodes, LabVIEW, and a single board.
See, it looks like playing a game, but here they are trying to control the. I hope you people aware of a game called Mario, which the kids will play in the system. Okay, so they'll be having a video game cassettes. And now they are moved into advanced like PlayStation and all. So before we have a TV video game where they have to put the cassette on the respective device and they can select different games. So in that there is a game called Mario where a man will be keep on moving to save a prince, okay, where he has to cross lot of hurdles and he'll be getting multiple powers in between. So that Mario moment we will control through joystick. But here if you see they have used LabVIEW FPGA, okay, they have used a single board Rio, okay, so that is a family of Rio hardware, and they have used LabVIEW FPGA, okay, to have a control. Okay, they are going to place these sensors on the near to our eyes, and and we know whenever the eye moves it get polarized, it is going to generate some voltage. That voltage information will receive and they'll process it based upon the eye movement. They're going to control the Mario movement in the video game. Okay, so it looks like a game, but they have acquired a real-time signal and they have processed it and they are controlling it, okay, through LabVIEW FPGA. Okay, you can watch the video now.
Rio to play video games with our eyes.
Did you know your eye is polarized? The back of your eye is more negative than the front of your eye because of a large population of neurons on your retina. As your eye moves, the electric field surrounding your eye will move as well. We can measure these voltages by placing electrodes on the left and right side of your face. So if I look one direction, we measure a positive change, but if I look the other, it'll register a negative change. Likewise, we can place electrodes on the top and bottom to measure looking up or down. Because the voltages we're dealing with are very small, there's a ground electrode placed behind the ear. This provides a reference with which to compare the other voltages. This type of measurement is called an electrooculogram.
Now that we have these electrodes on my face, how are we actually going to turn that into a Nintendo signal? Let's take a look. This is a custom Doppler card that we've created that has circuitry to filter and amplify that signal coming in. We'll then read it in on the bottom layer, which is the single board Rio, real-time computer, and FPGA. And on this Windows computer, we're able to display that data as it's coming in. We're able to send that data back out through our single board Rio through a custom cable we've made to our Nintendo.
Ah, we're doing so well. No.
Building electronic devices.
So this is also a small information where LabVIEW FPGA is used, okay, which is used for yeah, so which is used for application developments, okay. So you can use this LabVIEW FPGA for n number of applications. You can make use of this NI hardware for more application developments. It depends upon the requirement. Okay, so I think we are at the end of today's presentation. So this is my contact information. If you are looking for any support related to LabVIEW, right, NI hardware as well as software platform, technically, okay, any technical support, you can reach me through this email, okay, and you can text me through the number also. This is my contact number. You can have it for a reference. And if you have any queries related to LabVIEW, you can reach me. And for today's session, if you have any doubts, feel free to ask. Okay, so I want you people to work on these kind of industry hardwares. Okay, so you can just encourage your students as well as the research scholars to develop or do the mini projects or the major projects or the research works using NI software and hardware, which gives them a more weightage of the profile, and they can learn more thing related to industry. Fine. So if there is any query, please let me know, participants. I'm ready to clarify your doubts. Any queries? If there is no queries, please let me know.
Nagarajan sir,
Yes,
I
sir.
think there is no queries,
Okay.
so we can conclude the session.
Yes, sir. Yeah.
I thank you on behalf of Electronics and Communication Engineering Department, KLSGIT.
Thank you.
This was a very wonderful and informative session by you. Okay,
Thank you.
so
Thank you.
I thank you wholeheartedly, and I hope the participants have gained uh, better insight into the possibilities of the NI technology with respect to different applications. Okay,
Yes, sir.
so thank you very much, sir.
Thank you, sir. Thank you so much. Thank you, participants. Thank you.
All the participants are requested to give the feedback on the above link which I have posted.